Hello everyone. This video is in continuation of the previous video based on groups. In this video we are going to see some more example based on groups. Okay, so coming to the fourth example. Now here G is collection of all A, so that A is a 2 cross 2 matrix with real entries and determinant of A is non-zero. And A star B is defined as A into B, that is multiplication of matrices. Now to check whether this G comma star forms a group, we need to check four properties. So the first property is of closure property, that is if you pick up any two element A comma B in G, then A star B should also go inside G. So for that, let us have two element A comma B in G. So that will imply that determinant of A is non-zero and determinant of B is non-zero. Now what is A star B? A star B is A into B. So this A star B will go inside G provided determinant of AB is non-zero. Now for that we are going to use one property of determinant, that is determinant of AB is equal to determinant of A into determinant of B. Now since the multiplication of two non-zero real number is again non-zero, so this determinant of AB will be non-zero, hence this AB will go inside G. So the closure property holds. Next is of associativity, but we know that multiplication of matrices follows associativity. So this G comma star will follow associativity property. Next is to find an identity element E. Now the job of E is done by the identity matrix 1001, because A into identity matrix is same as identity matrix into A, and that is A. So the job of E is done by the identity matrix. So yes, identity element exists. Next is of finding inverse for every element. That is, if you pick up any A in G, then you are required to find another element B in G, so that A into B is identity. That is, A into B is identity matrix. Now, if you pick up any A in G, then that will imply that determinant of A is non-zero. Now we know that if determinant of any matrix is non-zero, then that matrix is invertible. Now invertible means there exists another matrix B of order same as of A, that is the order of that matrix B will be same as the order of A, such that A into B which is same as B into A, and that is identity I. So yes, for any A in G there exists B in G. Note that this B is in G because B will be having real entries and we are collecting all matrices with real entries. So yes, inverse element exists for every element in G. Okay, so this G satisfies all four conditions, hence we can conclude that G is a group. G comma star is a group. Now note here that multiplication of two matrices is not commutative. That is, A into B need not be same as B into A. You can take it as an homework, find such A and B. So we can conclude that G comma star is not an abelian group. So this is the first example of non-abelian group that we have seen. Also note one more thing. If we take G as collection of all 2 cross 2 invertible matrices with integer entries, then this G is not a group because it does not satisfy fourth property, that is inverse element does not exist for every element lying inside this G. For example, if you pick up A to be 2001, then this A is going inside G, but its inverse is half 001. This does not belongs to G because G contains all 2 cross 2 matrices with integer entries. So this does not form a group. Coming to the next problem. Here we need to prove that the set G, which contains 0, 1, 2, 3, 4, 5, is a finite abelian group under addition modulo 6. That is, A star B is A plus B modulo 6. Now, as this G contains finitely many terms, so it's better to draw a table, and it is drawn in this way. Now here I have written 6 is congruent to 0 because 6 is congruent to 0 modulo 6. 7 is congruent to 1 because 7 minus 1 is divisible by 6. 8 is congruent to 2 because 8 minus 2 is divisible by 6, and so on. So this is how we complete the table. Now if you observe, all the elements of this table is coming from G, so closure property holds. And also addition satisfies associativity, so this G comma star will satisfy associativity property. And the job of identity element is done by 0 because a plus 0 is a for all a in G. You can observe with the table. Okay, now we need to find inverse of each and every element. That is, if you pick up any element a, then we need to find b so that a star b is 0. Now inverse of 1 is 5 because 1 plus 5 is 6 and 6 is equivalent to 0. So inverse of 1 is 5. Inverse of 2 is 4 because 2 plus 4 is 6, which is congruent to 0. So inverse of 2 is 4 and inverse of 3 is 3 and so on. Inverse of 4 is 2, inverse of 5 is 1 and inverse of 0 is 0. So yes, inverse exists for each and every term. Hence this G comma star is a group. Also note that the table matrix is symmetric, so we can conclude that this G comma star is commutative. Hence we can say that G comma star is an abelian group. So now coming to the next problem. Now we need to prove that the set A, which is 1 2 3 4 5 6, is a finite abelian group under multiplication modulo 7. That is, A star base A into B modulo 7. Now again, as this A contains finitely many terms, it is better to draw a table, and that is drawn in this way. Okay, now as all the elements of this table are coming from A, so closure property holds. Okay, and as multiplication of numbers satisfies associativity, so this A comma star will satisfy associativity. Okay, now we need to find identity element. Okay, now here the job of identity is done by 1 because A multiplied by 1 is A always. You can observe with in the table also. Okay, so identity element exists and that is 1. Now next we need to find inverse. That is, if you pick up any A in A, then you need to find another element B in A, such that if you multiply A with B, then you should get 1. So here inverse of 1 is 1 because 1 multiplied by 1 is coming 1. Inverse of 2 is 4 because 2 multiplied by 4 is 8 and 8 is congruent to 1 modulo 7. Okay, and inverse of 3 is 5 because 3 into 5 is 15, which is congruent to 1, and so on. You can find inverse of each and every term. So yes, this A satisfies all 4 properties, hence this A comma star forms a group. Also, if you observe this matrix, the table matrix is symmetric. That is, this star satisfies commutativity property. Hence, we can conclude that this A comma star is an abelian group. Okay.